Yeah, in this lecture, we are going to start talk on Cepstrum analysis. Now, by now we have seen that there are many instances where signals are modulated. Okay, so and if you have modulations, we get sidebands on a signal. So if I have a carrier frequency and a modulated frequency, I will have frequency of these kind of sidebands around the signal. So, if I look in the frequency domain transformation of a signal, and so on, some amplitude. So, this is my carrier frequency and this is my the upper sideband and the lower sideband. Okay. So, detection of sideband becomes a problem. Why? Because in a machinery signal where we are measuring from a, say for example, a bearing location, there will be instances where there will be a lot of other frequencies in such signals. So, it becomes the detection becomes very difficult. So, this is another technique of detecting sidebands in a signal, and this is actually done through what is known as Cepstrum. Now, what happens? Let me tell you this. Suppose I have a signal in the time domain, some signal x t. Okay. If I convert them through FFT, so I will get a signal frequency. So maybe a real part of x f, which I will denote as x real, and the imaginary part of x f, which I will denote as x imaginary. So, FFT of a signal x t will give me a complex number x f, which can be written as x real frequency plus x imaginary frequency. So, this is a complex signal. Now, if I do an inverse FFT, I will go back to my original time signal, and so this is in, to begin with I was in time, I come down to frequency and I come back to time by doing what is known as an inverse. Let me write it here for the benefit of the camera, inverse FFT. Okay. Now, what happens is in this inverse FFT, we change some modules in the real and imaginary part. So, I have XR frequency plus imaginary x imaginary frequency. So, to this I give the logarithmic amplitude of the signal, and to this I make it a continuous phase. So, what is log amplitude of the signal? Is nothing but logarithmic to the base 10 of x f amplitude, where x f amplitude is nothing but x real square plus x imaginary square root. So, this is one argument. So, when I do Cepstrum, if I do log scale, I add this here, and for the continuous, if I have the phase is nothing but tan inverse x imaginary and x real phase. But you will see this phase is going to dance between minus pi by 2, phi, pi by 2 and so on. So, I can always make it a continuous function. This is a continuous function and which is known as phase unwrapping. So, phase will not jump, but it will have a continuous signal like this with frequency, because I need to give you a continuous signal. So, with phase may look like this. So, it is a continuously varying phase. So, this becomes the imaginary part and I have the real part as the amplitude of the signal, log amplitude. So, if I do an inverse Fourier transform, I will get what is known as the Cepstrum. But I will tell you how this logarithmic scale helps, and I am sure all of you know from your high school maths that log m times n is known as logarithm of m plus log of n. So, if you have modulated signals, so for example, I am writing an amplitude modulated signal where x t is equal to a m sin 2 pi f c t, where a m is nothing but some a sin 2 pi f m t. So, basically my x t is nothing but a sin 2 pi f m t times sin 2 pi f c t. So, there are basically two functions which have multiplied. So, if I do a logarithmic, they will get added. And what happens in Cepstrum is the effect of one signal or event on another is either added or I can also write subtracted depending on the sign. So, Cepstrum helps us remove the effects of any one signal. Okay. This signal, this effect could be, for example, Cepstrum is used to understand the seismic signals, understand speech signals, and in CBM understand gearbox signals. Now, because this is added or subtracted, I can very easily separate the sidebands by doing a Cepstrum analysis of such modulated signals, and as you will see later on, modulated signals do occur in gearboxes, and once we have the Cepstrum, they will look like this is known as the Q frequency. This is inverse of frequency, okay. And instead of amplitude, we will have amplitude. And so on. Okay. So, I will see a single line. So, this now is in time domain actually, if you see, because I have done the inverse from the frequency to the time. So, this is in seconds. So, some tau. So, the indication of this, the value of this tau will actually indicate the value of. Okay. So, the effects of carrier frequencies has been removed, and then I can easily identify the modulated frequency in a gearbox or in any Cepstrum signals. And we will see this with an example where we are using Cepstrum for CBM in a gearbox. So, there are many ways. So, power Cepstrum, somebody defines this as the log of this Fourier inverse. So, I had shown you what this f(x(f) looks like, the internal of it. So, one of them is the log amplitude, and other is the imaginary part is the continuous phase. So, detection of sidebands in modulated signals. So, I will just briefly give you an example of a cement plant where some data has been taken. The reason I am showing you this cement plant is because of the fact that we will be coming back to this cement plant again and again, and we will see a lot of things happening here. See, for example, the way the cement is actually manufactured is there is a big drum. Okay. This could be about very long. Okay. This could be about 10 meters. This diameter could be about 2 to 3 meters, and this rotates very slowly, about 2 to 3 RPM, and of course it is sometimes inclined, and then the raw materials for the cement like limestone, fly ash, etc. is added. Okay, and then there is a big grinding media, nothing but strong vanadium balls are there. So, if this is rotating on this drum, and of course the drum has a liner which will protect it against abrasive wear and tear, and because of this grinder at another fine end you will see the fine powdered cement coming out, there will be a sieve, etc. But the fact is this big drum has to be rotated from 2 to 3 RPM. It requires a massive speed reduction because the powering device is at this end, which is nothing but an electrical motor. Typically, this motor is of the order of maybe 1000 kilowatt, 1 megawatt, and so this usually runs at about 1400 RPM, 1440 RPM, and for this massive speed to be reduced, we have 1440 RPM here to about 3 RPM here. So, there is a substantial speed reduction in a 3-stage gearbox as is shown here. So, all these gears, these are actually nothing but the pinion and the gear, and they are supported on bearings. So, if I want to do CBM on this gear box, I have to actually capture the signal from accelerometer put on this bearing in this gearbox, and the output shaft of the gearbox actually connects to a torsion shaft. Okay, and torsion shaft is a weak structural member in the entire system. So, if the this is very weak, so if it breaks, it will fail here, and this can be replaced and so on. And then this is supported, this is driving a pinion, okay, or and then this is driving a crown gear or a ring gear, which is mounted all along the circumference of this kiln or the drum, and this is supported on bearings. Okay. So, we have some vibration signals taken from the entire plant, and I will show you how sidebands occur in such gearbox signals. So, this is a little specifications of the cement plant for those of you who are interested to get an order of magnitude feel. This is about 2.5 meter in outer diameter, it is about 12 meter long, and it is about 70 ton. The girth gear on the girth pinion, okay, you can see it has 150 teeth, 21 teeth is the pinion, is a torsion shaft, as a gear coupling which is driving the torsion shafts and the gearbox, and then in the gearbox itself stage 2 gear, pinion, etc., all these modules are there. Is an electrical motor of, in this case it is actually 600 kilowatt and 985 RPM. There are few bearings, and then of course the grinding and the mixture medium material in the medium is about 39 tons, and then we get about 4 tons of cement, and cement material flow rate is about 12 tons per hour, and the drum filling ratio is about 25 to 40%. So, this works around the clock with this kind of operation being occurring, and of course we have many cement plants in our country which run off the fly ash from power plants and so on, and this is used to make such cement. And if I show you, because I was talking about data recording in the previous class, if you see this is the girth gear, okay, and right here, and this is the drum which is actually rotating, and this is the torsion shaft and the coupling. So, if you see here, there is an accelerometer on either sides, and these are the long cables which go to the accelerometer. And obviously, this is a very dusty environment. So, any sort of signal analysis is actually not very convenient or possible. So, we record the signal. Okay. And this is a view of a 3-stage gearbox. Here you will see the electrical motor, which is about driving this input shaft, intermediate shaft, and the output shaft, and this shaft is driving the torsion shaft of the cement plant. And this is the same data recorder, and you will see this is a typical data tape, okay, where there is a spool, okay, and this you can record about 90 minutes to 60 minutes depending on what speed you are recording the signal. And the same tape recorder was used to record 8 channels of vibration data. And this is just to give you a relative feel of the dimensions of the cement plant mill we are talking about, because one of my students worked on a rigid body model to understand the dynamics of such a cement plant. So, I have this here. This is the rotor shaft, okay, which is driving the gearbox, and this is the torsion shaft, girth gear, and the girth gear pinion and the gear shaft. Okay. And this is a typical vibration spectra of all the 8 channels which are recorded, and this is up to 1.2 kilohertz and so on. And you can see this is up to 2 kilohertz, and you can see these frequency spectrum, that you will see there is a lot of stacks of side bands, okay, which is normally not possible in a fast Fourier transform, and that is why in fact we are doing Cepstrum analysis. Okay. So, if you will see this is the typical signal frequency vibration spectrum of a gearbox, okay, and so on. So, now you see this is the vibration spectrum here, okay, and you see there are so many side bands, okay, of this multistage gearbox. But if I do this Cepstrum, I will see a peak, and if this is in time domain, this time actually corresponds, this value in the time actually corresponds to the frequency of rotation of that particular gear near that bearing. Because see, in this signal let me tell you, particularly in CBM, as you will see later on, whenever we capture data from any machinery, whatever be the shaft, it is actually at this bearing locations. Okay. So, this is the bearing location. So, when I record a signal, it is a composite signal. So, there could be bearing faults, there could be bearing faults, or gear faults. Okay. So, how can this be reduced? So, obviously, you will later on we will see, when you do the frequency domain transformation, you will see a lot of peaks. Some amplitude. So, Cepstrum is going to help you. If I do a Cepstrum, it is going to maybe this, you will see one peak, okay, and this time period, this is in time, and this is the Cepstrum. So, this time period tau is nothing but 1 by certain f, where f is the predominant sideband in the signal, okay, like an amplitude modulated signal. So, this is what we actually found from recording the signal of this gearbox using this 8-channel data recorder. This is another spectrum at the girth gear support. Okay, you will see a lot of peaks here, okay, which is very difficult to identify which one is from the bearing, which one is from the gear, which one is for other machine rotor problems like a cracked shaft, like a misaligned shaft, like an unbalanced shaft. So everything is a composite spectrum is what we get actually physically. So to reduce this very easily, we can do the Cepstrum and just find out the very important peak which corresponds to the rotational speed of that system. Okay. Another, at gearbox base, you see a lot of sidebands are there. Okay. So if somebody asks, what are the frequencies, it will be very difficult. But if you look at these peaks here, and sometimes some of them have harmonics, okay, you will see that this length, this distance is actually in time domain. This is in frequency here, this is in time domain here. So this time is inverse of that would be the speed corresponding to that device, and this is how Cepstrum actually helps us remove the effect of one signal over the other. Okay. And if you will see on motor and gearbox analysis only, the signals are kind of little different. Okay. So this kind of analysis helps us find out the faults in the system. So we will later on, of course, you will see how a bearing fault can be distinguished between a gear faults, but I will right now tell you a gearbox fault is actually manifested in increase in the amplitude of the side bands. Okay. So this can be, unlike a bearing fault, which may have frequencies, we will discuss this later on, but I just wanted to drive frequencies at characteristic components will show increase in amplitudes and very high frequency vibration. We will discuss about this later on. Okay. Now, I will give you an example of this gearbox if you do a Cepstrum analysis, just for the sake of discussion. For example, if I have a gear driven by a pinion, okay. So this is N1 T1 and this is N2 T2. From the law of gearing, I have N1 T1 is equal to N2 T2. For the sake of discussion, if T1 is say 100, T2 is say 25, N1 is say 1200 RPM, your N2 is nothing but 1200 times 100 by 25. This is nothing but 4800 RPM. So in this RPM corresponds to 1200 by 60, that is 20 hertz, and this is about 80 hertz. So that means this gear, which has 100 teeth, is rotating at a speed of 20 hertz, and this pinion, which has 25 teeth, is rotating at 80 hertz. So if I put this in a casing and put a transducer and take a signal from such a gearbox, I will get a signal like this. So, if I do the FFT, I will see a frequency of, this is nothing but the GMF, which is nothing but the gear mesh frequency, which is nothing but 20 times 100, because 100 teeth. So, this is about 2000 hertz. So, around 2000 hertz, this is in frequency, I will see sidebands corresponding to one corresponding to the gear and other corresponding to the pinion. So, this spacing here in one case will be 80 hertz, in another case this will be, the closer one will be 20 hertz. So, if the sidebands increase at 20 hertz or 80 hertz, I may be able to detect it in a FFT, but if I do a Cepstrum, if I see a peak, because this is in time domain. So, this corresponds to 1 by 80 and this corresponds to maybe 1 by 20. I will say, there is a fault at 1 by 80, 80 means our pinion has a fault. So, this is the advantage of Cepstrum, and in real world this is a very noisy signal like this. So, Cepstrum helps us identify the sidebands in a signal. Okay. So, well, there are resources available on this in my book. Thank you.